So welcome everybody. I was told to say the meeting is being recorded, so it's being recorded. We are proud and happy to have with us Professor Emma McCoy. She's the Pro-Director for Education and a Professor of Statistics here at LSE. And she's going to tell us about data for a decision. And if you look at her research, you'll see that she's used lots of data for many interesting questions, such as earthquakes, do speed cameras reduce road traffic collision, the effect of the mode by which you travel to work on your skin, fascinating. Causal effect of road network capacity expansions on traffic volume and density. So when we expand, does it affect the capacity? And I cannot wait to hear what more she has to tell us. So,
thank you very much, and great to be here. I guess, have you had one of these Women in Maths events yet? Am I the first? Have you had how regularly do these run?
Oh, we've run them for 6-7 years now.
Yeah. But this term, I guess, this academic.
First
term. Okay, excellent.
We do one term.
I will find a way of being first. But no, great to hear that these are going on. And yeah, so I'm Emma McCoy, the new Pro-Director for Education. I was at Imperial prior to joining LSE. And, I first joined Imperial as an academic member of staff in 1996. So I was kind of Imperial through and through, really. So I'm looking forward to finding out more about LSE. I guess obviously the big difference is the fact that the disciplines that are studied here are so different to those at Imperial. But of course, there's a stats department, which is just fantastic, and a maths department. So great to be. I'm not going to just be coping with qual. I have some quant as well. And in fact, I have had very positive comments about my maths skirt today. However, I've also received some kind of less positive comments at a couple of the wider school meetings. So I'm kind of like, surely this division doesn't really exist, but maybe it does. So yes, that's me. So I do want to give a kind of a quick overview of my career. Now, I was kind of hoping that there was going to be some undergrads attending, but I don't know, what's the balance normally? Okay, who here is a student, first of all? Almost a PhD or masters? Very few of you. Okay, so, and a few more over there. So this talk was expecting maybe some more undergrads, so apologies in advance, and I will just kind of beef up the content, I think, as we get later on, because I think probably a lot of these things you will have seen before, but I am really going to concentrate on the work that I've been doing in observational data, particularly that around transport, and you've already given some titles of the kind of data that I work with, but I will say a few words about my career, and Nick is here as well, who I have known from Imperial for more years than I would care to admit. So great to see you here, Nick, as well. And you know, all of the lies I was going to tell about Imperial now, I have someone that's going to correct me. So obviously, the nice thing about joining LSE is it's rooted in this whole idea of what the causes of things, and it's something that I've really become interested in over the last kind of 10-15 years in relation to data analysis, particularly around all of the movements, I suppose, in data science and some of the issues that you have there with some of the approaches that are being taken. So I'll briefly kind of whiz through the potential outcomes framework, which I'm sure you're all familiar with, and then move on to some of the work that I've been doing using propensity scores in these observational data sets. And then we've got quite a few applications that I'll whiz through in the end. So in terms of my career, as I said, I came back to Imperial post kind of a postdoc in the States in 1996, but my statistical career really started, and at the fault, I can blame most of my career really on Bernard Silverman. For those of you that don't know Bernard, he's a very famous statistician, did a lot of work in computational statistics, and he convinced me to do an MSc in computational stats at the University of Bath a very long time ago. He then went on to become, do a lot of government work in terms of being taking the CSA role. He's still doing a lot of work now on modern slavery, which is really fascinating if you go and have a look at some of the work that he did that came out actually of the work that he did whilst he had his role as Chief Scientific Advisor.
What's CSA?
Pardon?
What is CSA?
Chief Scientific Advisor.
Oh, Chief Scientific Advisor. Sorry, I'm kind of acronym central. Yeah. So he basically moved from I think he was at Oxford for a while, at one of the colleges, and then he moved into government for a long time, doing a lot of the advice on statistics. Did some really interesting things there. Then I moved to Imperial to do my PhD under the supervision of Andrew Walden, who's recently retired. Then at that point, really quite much more kind of theoretical work then, did quite a lot of work in wavelets. And when I first arrived at Imperial, Adrian Smith had only been there for kind of maybe a year or so. And he then became the head of department. And it was a time that was really active statistically at Imperial. It was kind of an amazing place to be because we had a big group there. And it was built initially, of course, by David Cox, who unfortunately died relatively recently. And David Cox, he did say to me once, actually talking about the women in maths, he generated the most amazing number of academic female statisticians, quite remarkable. So when I joined Imperial, having been in a very male-dominated environment when I was in Bath, came to Imperial to do my PhD, and there were several senior academic statisticians that were women, which I think was quite exceptional at the time, and they'd all been supervised by David Cox. And I'm still in touch with many of those amazing women, and when I spoke to David Cox about his influence there, he said, oh, well, women are just easier to work with, so we have a mixed audience with. So, which I think was quite an interesting statement. He was saying that he found men way too competitive, and he just found it much more collegiate working with women. So this is being recorded, isn't it? I can't believe I'm saying all these controversial things. You'll find out that most of what I say is said with a hint of humour. And of course, interestingly, the dichotomy there, of course, is that I really enjoy working with men because that's what I'm used to and done all my life. So it was quite surprising to suddenly find myself in a much more mixed-use group. But well, just within the stats section, there were very few female academics outside statistics in the maths department at Imperial. So statistics is a section within maths at Imperial, which is quite different to here, obviously. And of course, Adrian did some amazing things in MCMC and Bayesian statistics, and carry on and is still working to this day, current president of the Royal Society. So as I've already said, I kind of then found myself in New York doing a postdoc, again more on kind of wavelets and time series. And then Adrian Smith contacted me to say, do you fancy a temporary lectureship in statistics? Because they had John Wakefield, who is now in Seattle in Washington, at the University of Washington. He was doing a secondment within Imperial, but working with the EPI group, trying to bring together some of the more biostat stuff with the statistics section. So I came in to fill for him, and then I didn't leave until 3 weeks ago. So that was pretty much, and then I did pretty much every administrative job there is known to mankind in the maths departments at Imperial, so I have huge sympathy for those of you that are heads of departments and program leaders and admissions tutors, and hopefully that will help me as I kind of navigate my role here, because I think I do have an understanding of what it's like to actually work within a department and try and deliver high quality education when you have people like me coming in and interfering from the top. So hopefully we'll find ways to work constructively together. So in terms of data influence, I do want to kind of highlight a couple of points throughout my career where actually my training in statistics and mathematics actually stood me in unbelievably good stead. So as admissions tutor, and this again is related to the women in maths issue, we discovered that there were, I just cannot help but really dive into data whenever I have it. So I started looking at our A-level data when I was admissions tutor. I did all the work that talked about the meaning of an A-star when that was first introduced and the influence that had on maths and further maths on outcomes. I also discovered that we saw quite a big drop in our female admissions from home students. And then that turned out to be associated with, I need to be careful with my causal statements here, but it turns out that there was certainly a correlation between those students that, the female students that were applying generally had double maths, they all had maths and further maths. Often they took a third A level that wasn't physics, for example. Some of them would come in with a French A level or English literature or more broad. Basically, they weren't even getting through our first filter stage because we were preferring physicists and chemists to those that had a broader base at A level. So we've actually now changed that so that we are quite cognizant of the fact that you may be getting some biased admissions if you start taking those kind of decisions, and we were really missing out on some good students. I was also heavily involved in our what's known as the Access and Participation Plan, and that's something that we have to do here at LSE this year, and it's just around what you're doing to support widening access for students into university and then being able to participate successfully when those students arrive. So I'm sure you're doing quite a lot on kind of WP, you've got contextual offers and so on at LSE. But I did quite a lot of work with that data at an institutional level at Imperial, and so basically I did the stats that went into the plan that we put forward, and it actually led us to develop some of the scholarships that we had for Black heritage students, because what it turned out at Imperial is that we were rejecting a lot of students, a lot of Black heritage students that then went on to meet our entry grades. Unbelievable biases that exist. So we did quite a lot of work to kind of try and get some balance in our access and participation plan. So I do think that having that kind of mathematical training, I think, has been really instrumental in, I think, helping me to kind of progress in my career. It enables me to really weigh up evidence, which is pretty much what we do on a kind of a daily basis. Well, in fact, what's been interesting here is I'm now going through what are known as the annual monitoring meetings with all the departments, and it's been fantastic seeing the difference in tone between the different departments, and it's such a broad range. I'm kind of absolutely loving, I am actually loving some of the narrative around some of the submissions that come in. I should probably add that I am kind of the black sheep in my family. My mum is an English teacher. My grandfather was a mathematician. He worked at GCHQ, but my mum is an English teacher, and I am her biggest disappointment, is what I have to say. She's just so disappointed that and then I get together, and my sister as well is kind of, I would say, more towards the arts and literature than I am. So I get together and they're always describing the latest book that they've read, and I'm always wanting to talk about the latest theory I've proven, but there you go. So they, as I say, I am her biggest disappointment. So my close collaborators now are still two are at Imperial, so you can see there's Dan Graham. Now, one of the things that I think certainly has shifted in my career has been trying to work on real problems that require solutions. Dan Graham is a professor in civil engineering at Imperial, and he is the director of the Transport Studies Group. And the story about how we started working together actually was that he'd been kind of wanting some stats help, and then it turns out that I was at that point starting to cycle into Imperial, and he was saying, I do whole loads of, I do a lot of work on accident data, so I was like, oh, that's great. How can I plan my route kind of thing? Let's talk about it. And then that turns into a very long-standing collaboration that's really driven by purely selfish means, really, in terms of how I get to work without killing myself. And then I started working more with Audrey Nazal, who's based in the Centre for Environmental Policy, and a lot of the work that we've been doing is around air quality and data and traffic, and she's got access to some fantastic data that I spend a lot of time poring over. And then Brian is one of my, he's actually been in industry for several years, but he's now doing a PhD. He works for ASOS, So we're doing quite a lot of work in controlled experiments with his ASOS data, which is an online retailer, for those of you that don't know. So I have certainly shifted from being, I would say, more theoretical as a PhD student to actually now trying to solve real data, real questions that arise from kind of data that we collect in such great volumes. And of course, a lot of that data comes from observational studies. We've got lots of data on cycle. Dan in civil engineering, he has such amazing data, it's just a dream. So he works a lot with TfL. We've got the underground data. Irritatingly, it was great when we used to have Oyster cards, but now they've shifted to people just using their own cards. You can't track longitudinally in quite as consistently as you used to be able to. So I used to be able to, I basically just can be fascinating watching how people use the tube, how you can take 25 minutes to go from Leicester Square to Covent Garden has always bemused me, goodness knows what they were doing underground for that length of time, which again goes to speak to data quality when you're trying to work out journey times and so on. Another data set that I find fascinating is Strava data, and I'll come to that a bit later on. Stats 19, this is all of the accident data that I obsess about. And then PASTA data was a big European study. This is the kind of thing that we can't be involved in anymore, of course, now that we're no longer in Europe. But it was around physical activity, and it's a fascinating data set where they have several cities involved, and they gave everyone sense-wear, and then they wear it, and you can track them with GPS, and you can. But then, of course, they kept diaries for the first week. And then after that they didn't, so they're just wearing the sense-wear. And trying to ascertain what transport mode they're using is a kind of a big statistical problem, and then also the health data as well. So we have all of their heart rates, we have the galvanic skin response, which is a measure of stress, and so on. So there's some very nice data that now, of course, now I've moved into this role, and probably the last few years at Imperial being in a more kind of an education-related role, this all gets done kind of at the weekends and in the evenings. The role here is kind of full-time on education, but I think that there's probably, hopefully, quite a lot I can bring from I guess, my statistical expertise to some of the issues that we're facing here as well. So another thing that I found quite interesting is, and I think that this is getting worse, of course, with the kind of social media and misinformation and so on, but this is the kind of thing that I read the papers and my blood boils on a daily basis. So literally, I can't remember which paper this was. I'm probably got it listed somewhere. There was a period where there appeared to be lots of cyclist deaths, and then people just look at the raw. There were 2 this year, and then there were suddenly 30 the next year. And then they'll make these claims like, why are you 17 times more likely to be killed on a bike than in a car? Those kind of statements drive me a bit mad in terms of the misrepresentation of data. And so I guess my questions then become, when can these statistical statements actually be trusted? And I have quite a lot of interest in the kind of ethical use of statistics as well. So here we go. Can anyone tell me what that is? What does that look like?
That looks like the rubber taps.
It does, yeah. So this is actually, I've amalgamated all of the road traffic accidents, I'm obsessed with road traffic accidents, from over a 7-year period, from 2001 to 2007, and it's a dot. This is actually the dots. So you can really dig into this data in terms of where there are the big accident kind of hot spots. You get these. So I live kind of somewhere up here, and I used to need to get down to kind of down here, which is where Imperial is. Sorry, you guys can kind of over there, won't be able to see this. And now, of course, I've got an easier route straight into LSE, but I still need to get through this bit here, which can be fairly grim in terms of how dangerous that particular area is. But this data is, well, I don't know, why not? I'm going to get fairly morbid as well, but it's kind of quite fascinating. This is all amalgamated, so this includes the data where you have a serious accident, where you have a death, which thankfully there aren't that many, but anything that's reported to police is in that data set. There are also some in rather, so clearly data quality issues as well. It's generally not bad data, but you'll see, I think there are actually some accidents actually happening in the Thames and things, and you get which is kind of, there you go. Mainly not, but you can see some of the very dodgy bridges. Anyway. So another data set that I kind of like, that I have, well, Strava have now got very expensive at selling their data, but there was a period when they were first introduced where they gave their data more freely for analysis. And this is the 2015 Strava cycle heat map. So you can see where people in London are cycling. So I don't know, are there any cyclists in here?
Yeah.
Ah, yeah, okay, great. So you can see people kind of doing madly lapping Regent's Park and things like that, you know. Now, I cycle, and in fact during lockdown I cycle a lot more, but when this data was collected, I was cycling, but in a more kind of pedestrian way. But I do run, as Nick knows. Nick and I used to run together quite a lot. I don't run actually, I've not been running so much anymore. But so anyway, I used to run, and I used to have one of these sports watches that you used to have to swap between. You have mode where you could switch between cycling and running and so on. So I'd have it on, but I always had it on run mode just because it's too much hassle. But I always used to record my cycling accidents. So this data will include me. Well, no, on the run. At the moment, this is the cycling heat map. But if you look at the running heat map, some of that will be me running incredibly fast because I'm on my bike. so in fact, somebody did eventually message me on Strava to say, you know, do you need a running partner? I think there was somebody that thought, and then I had to say, no, that's just me cycling very slowly. It looked like I was doing three 30-minute Ks kind of along around Regent's Park, but I was actually just cycling slowly. So, but nonetheless, I've spent a lot of time on my own data, and when I was at Imperial, I used to have the first year data challenge. So I used to give my running, I always used to do a 10K race in December. And I used to give all of my training data to the first year undergrads, and I used to have a prize for the person that predicted my race time. So it was always quite an entertaining little data challenge that I used to run every year. And they used to be able to look up the weather and the wind and all of that. I mean, people did it, the students did a kind of an amazing job. Anyway, it was kind of fun. Right, so as I say, most of my, it's making it sound like most of the work that I do is purely selfish. That's true. Maybe that's true. But anyway, these are just some examples of some of the bike accidents. So I do genuinely plot my route based on this information. Similarly, speed camera locations, less important for cycling, but I do look at trying to optimize my route. I run these rather bizarre experiments. I think I am rather tragic, actually. So, well, I'm admitting that. But I run these little experiments with my routes because, of course, you've got loads, so I kind of, well, at the moment, I have a route that I've done it 8 times, and I'm going to do it 10 times for my little experiment before I do a new route and figure out my average times. This is rather tragic, isn't it? Anyway, I will say no more on that. But pretty much data has driven every decision that I make. But I can probably say that I will have a better route from my house to here than pretty much anyone else, I would guarantee, by the time I've finished my experiments, which may take me a couple of years. Right, so lots of causal questions that you can dream up here, and the ones that we did actually look at were things like effective speed cameras on the number of accidents. There'd been a lot of negative press if you go back to, well, you know, kind of 15 years ago or so, where people were saying, oh no, speed cameras actually increase accidents, those kind of things. So we were trying to get some statistically sound analysis of these kind of questions. Similarly, when they were introducing bike lanes, there was quite a lot of push against the introduction of bike lanes, actually just increase kind of air pollution, do they decrease traffic flow and so on. And then another interesting one that Dan Graham and I worked on, because of a particular question that he'd been posed by one of the London boroughs, that was around, do you see more accidents? Because anecdotally, there had been more accidents in areas where you have kind of higher levels of kind of inequality, when you have more deprivation. And of course, the reasons for that are varied. So the first, Dan and I had a discussion about why would that be. When you're doing these causal, when you're asking these causal questions, the first thing you obviously need to do is draw your directed data. You draw your DAGs and you try and think of all the possible things that could influence your outcome. And then we were kind of laughing about the fact that even things like having a garden, would that have a, you're getting more children playing on streets, and South Kensington, very few child pedestrian accidents in Kensington, but a lot of those, even the wealthy, don't necessarily have gardens, but we were kind of saying maybe they're all parents have their kids on these reins or something, until they're 18, so you tend not to get these. Whereas, if you're in Hackney or something, you're kind of free to, my kids certainly were pretty much latchkey kids. I think they were out playing on the streets from when they were quite young. So there are all these kind of questions that come into it, but of course then there's the road network, less if you have less investment, less street calming measures, all those kind of things really impact these things. And then another one, actually, I'm probably not going to talk about here, but we've done quite a lot of work on cycle superhighways and congestion and so on. I'm still also, so on that, I'm working with Prajamitra, one of my ex-postdocs, who's now at Queen Mary's. Dave Stevens, I still continue to work with, he's now at McGill. And of course Dan, who has become a very good friend, and I constantly talk about transport with him, amongst other things. And of course the major issue in all these observational studies, as I'm sure you're aware, I'm at LSE after all, is confounding, where your measured treatment effect is explained by another unmeasured, often unmeasured factor. And there are some great websites on this kind of spurious, these spurious correlations, which I find pretty entertaining. The one that I tend to use on the students here's the obvious one, having a cigarette lighter in your pocket gives you lung cancer. That's a good one. But how about this one? Does anybody know what we've got going on here? Age, yeah, exactly. You've seen this before, right? Having bigger feet makes you a better reader. Babies tend not to read that well. But nonetheless, with the kind of data that I'm working on these unmeasured confounders are kind of the issue, as well as the measured ones. And sometimes they're really quite surprising how they might actually kind of arise. So for the accident data, I was talking about drawing these DAGs. I spend a lot of time drawing directed acyclical graphs. Another fun bit, literally. How my family puts up with me, I really don't know. And whenever something comes up, even at home, about mortgage rates or something, they're all like, oh God, here she goes again. Drawing my little kind of how all the conditional dependencies go. So, as an example, if you're after your accident rate, of course you've got a lot of things, traffic volume. This Operation Safeway is something that's kind of the police introduced to try and reduce the number of accidents, where they basically stop people and say, you should have lights on, you should wear a reflective jacket. And they still do it, I think, at these kind of blocks of interventions where they try and make a difference. But then obviously the speed cameras, and some of these arrows are pointing all over the place because it's in terms of where you think the conditional, where you think the dependencies might exist. So something that I just is interesting, and there's a question for you on the academic staff in terms of the stats side particularly. Do you teach potential outcomes to your undergrads? Do you teach the kind of rebind? When is this taught? It's kind of interesting.
The postgraduate.
Postgrad?
Yeah.
Okay. Because similarly at Imperial, it wasn't, we just taught all the statistical modelling, some really advanced modelling, but at no point do we actually, we talk about, we kind of say correlation does not talk, causation and correlation are different things, but, not necessarily one doesn't imply the other. But we don't actually talk about the framework for what that actually means. And of course, I'll get into arguments now if Phil David was here, because he thinks about things in a slightly different way. But I personally really like this kind of framework that you have two possible treatments, obviously. So if we think about binary treatments, you either get the treatment or you don't, and then you have an outcome. And then if you've got a whole bunch of subjects and the treatment, then you have these two potential outcomes, either your outcome if you're not treated or your outcome if you are treated. And then of course we want to find out the treatment effect, which we'll come on to in a second, but the issue that we have is that we only observe one of these outcomes. I mean, ideally we'd like to, you know, for every cycling, well, this probably is unethical, right, in terms of, in a lot of cases. But if we could wind the clock back and then repeat the experiment either in the untreated state or the treated state, then this wouldn't be an issue. You'd just be able to measure the treatment effect directly. But of course the issue is you only measure one of these outcomes, which you can write as just in terms of the indicator variable for treatment here, being that D factor there. And the unobserved outcome is known as the counterfactual. So this whole counterfactual thinking really is very interesting, I think. Now, you've got the population level. So this is another thing, of course, is that I am talking here about population level effects, and I know that there's obviously a big movement now to kind of personalise medicine and so on. So there are some interesting questions around how we do clinical trials, but that's a different matter altogether. But you've got your average potential outcome, so the expected value of Y0, which is the outcome if you're not treated, and the expected value of under treatment. And the average treatment effect is just the difference between those two things. And then you can see if your treatment actually worked or not. Okay. But you can also look at things like the average treatment effect just for the treated group and so on, and you might be interested in either of those. Now, so to try and answer that question about treatment effects, the fact is that these measurements, you know, it's very, you get a whole load, well, maybe I'll talk about randomized controlled trials first to kind of help us frame what the problem is with observational studies. Is that to actually be able to estimate the average treatment effects, generally, certainly within medicine, randomized controlled trials are kind of the gold standard, because what you do is you can ensure that your treatment status isn't confounded with any covariates, whether they're measured or unmeasured. And then that means you can just estimate your treatment effects directly. Now, it's a very, very powerful tool, but of course that's not to say in any particular trial these things aren't, you're going to be able to measure these things without bias, but obviously if you go through all of the maths, in a randomized control trial setting, you are able to estimate these treatment effects without bias. Anyone know who this is? Okay, but who would you say is the most famous statistician? This is Fisher. So Ronald Fisher, of course, he didn't invent randomized controlled trials. I think that was, I can't remember his name now, Bradford Hill, was it? Although that now we have to think about, is that really the person that invented them? But anyway, Ronald Fisher Fisher popularized the idea of randomized controlled trials in experiments. He obviously has come under, he was also heavily involved in eugenics. He's, you know, he wasn't necessarily a very nice person, I have to say. And he made some pretty awful statements about race. He also strongly believed that smoking and cancer were not related. He also had a lot of his research, I think, funded by some big tobacco companies, so there might be something going on there.
What time did he work?
Pardon?
What time in history are you talking?
Oh, so sorry, he was born, I think, in about 1890. Died in, I think, 1962. He was kind of, I think, in his 70s when he died. So you're talking about relatively recent history.
And then a lot of his work was, you're talking about his 20s, 30s.
Yeah. And he was at UCL when they had the big centre for eugenics there. So he was a professor in eugenics. It's when those kind of things were considered acceptable. But I think that there's probably been a bit of rewriting on history about that, but I know that the Royal Statistical Society kind of then made a decision to not, I think we probably had lots of awards and rooms named after Fisher at UCL that they've now renamed, and certainly at Imperial, I think we used to have a Fisher lecture theatre that's now been, I think now we give everything numbers, which is just easier. Probably sensibly, because I think it's quite difficult. I think it's a very tricky one. Because whilst obviously he's an amazing mathematician, we shouldn't have things up that kind of glorified, given his history as well. I think that we need to be very careful about kind of how we glorify the person, whilst we can still acknowledge the amazing kind of contributions that he made to the subject. But he was also, there are lots of reports written of him, and in fact I've spoken to people that kind of know him. Nick, did you ever come across
Last night. But I knew people who knew him. Frank Yates, for example.
Yes, indeed, because Yates, there's quite a lot written about Yates and Fisher. So it's kind of, I think that he ruled with a bit of an iron kind of, you know, he was at Rothamsted, so he was doing quite a lot of agricultural experiments. Very interesting kind of, amazing mathematician, but dubious human being. Again, this is being recorded, isn't it? So he actually popularised the use of randomised control trials as a way of coping with this confounding. Because it doesn't matter, because you'll then be randomised across the groups. It doesn't really matter if you've got confounding in those cases. And so, as I've already said, observational studies treatment selection is influenced by your subject characteristics often. So your baseline characteristics in your treated group are going to differ systematically, or can differ systematically from the untreated group. And now, of course, historically, you can take that into account by putting your confounding variables in as a factor into your regression. So you take an outcome regression approach to control for that. So these are called outcome regression models. But I'm going to talk a little bit about alternatives based on the propensity score, and also some of the work I've been doing on doubly robust methods. So, in summary, mathematically, in randomised control trials, the treatments are assigned randomly. So that means that the big deal here really is that your treatment effects, or in fact your average potential outcomes, are exchangeable. So given, you know, they're conditionally independent of the treatment here, which means that the expected value of your outcome, the conditional expectation of your outcome given the treatment, is just the same as the unconditional expectation. So in a randomised controlled trial, at least asymptotically, your ATE, your average treatment effect and your average treatment effect of the treated coincide, and you don't have to worry. In observational studies, there is no randomisation, and there are questions about, you know, the ethics around randomisation anyway, because you are obviously randomly allocating some treatment, but it's something that's accepted in medical trials, much less so in other trials. In the States, they do loads of RCTs for education, for example, but here we tend not to, because of the ethical issues, I suppose, that raises, where you're kind of having an intervention on some students that you're not offering to others. But I think if you want to make an informed decision about things, then it's kind of sensible to think about your design.
So in medicine, you can have a placebo for the control group, I think?
Yes, you'll know.
But
Yes,
how
yes.
do you do that in education?
Oh, well, this is a good point. I suppose, is there equivalent placebo? So you either treat or don't treat, probably. What could be a placebo in education? Sorry, Paul.
Well, in educational research, usually they don't have an alternative for the groups that are not receiving the interventions.
You just have an intervention or you don't, right?
And
But no, some people, they do have studies where you have different interventions.
nowadays, you need to justify your ethics by saying that you're doing something else to the group that you're not treating with intervention,
Okay.
just to compensate the disparity that you introduce.
But then how do they measure, how do
It's
they
not-
take that into
It's
account?
not
with
something
the-
that is directly related to the type of intervention.
Oh, I see. Right, okay. So they'll do some other good thing for that group.
It feels like a way to ease your conscience.
It's just ease your conscience rather than actually, okay, that's interesting. And I know actually also they have been doing some work in I was at a causal inference conference in the States, and they were talking there about kind of, obviously they have the studies where they stop as soon as they see some effect, right? So obviously they have these stopping rules as well, more than we might have, different levels of how you might assess your evidence, I suppose, as well. But of course, in observational studies, the big issue here is that this conditional expectation, given your treatment status, is not the same as the thing that you're trying to measure. So you're going to get biases. So propensity score, I think, is a really neat, there are some issues with it, right? But it's a very neat way of addressing some of these things, because your propensity score is nothing more than the probability of treatment assignment conditional on baseline characteristics. And I say here it allows us to perform analysis of observation study that mimics a randomised controlled trial, and I'm going to caveat with the fact that you need to have all of your confounders in your base. You need to have no unmeasured confounders. That's a pretty important difference, and actually guaranteeing that is quite tricky, but nonetheless it's still a very useful measure, because it actually also helps with some of the dimensionality issues that you have with outcome regression models. I'll come on to that in a second. But it's effectively a balancing score. So what it means is that conditional on your propensity score, conditional on that probability of treatment, the distribution of those baseline characteristics are going to be similar between treated and non-treated subjects. Now, I mean, this has been around for quite a while now, kind of seminal paper of Rosenbaum and Rubin, that define the propensity score in this way: the probability of treatment given some covariates. We're still talking about our kind of either treated or not, this kind of binary treatment. And of course, conditional on the propensity score, the covariates match the treated and untreated. So you can run some simulation studies to show that this works pretty well, where your propensity score is where there are no unmeasured confounders. Now, of course, in the randomised controls trial, your propensity score is known. That you just know, because you have allocated the treatments, right? That's the whole point of a randomised control trial. But you need to estimate the propensity score in observational studies, and that's what I try and think about. Now, if this is a very, very, very strong assumption, but I'm going to just kind of work my way through this now, and then we'll talk about the issues afterwards. But if strong ignorability holds, which means that given these covariates, then you get that conditional independence of treatment, right? So conditional on these covariates, you get that conditional independence, and in fact if the propensity score is not 0 or 1, then you can obtain unbiased estimates of the average treatment effects. And there's some lovely work of kind of Rosenbaum and Rubin. It's a lovely paper in the early 80s, loads of work done since. So the idea is that you have, I was say this first condition actually says that you have to have no unmeasured confounders. So it's this given X here, right? You have to have all of your confounders in here measured. So the idea of propensity score matching, which is the one that's used the most often, is you basically just match subjects with a similar propensity score, because then they'll be similar in terms of their covariates. And then you can just use that data to estimate your average treatment effects. There's lots of software to do this automatically. I think there are some big problems with this propensity score matching. I prefer actually to think about it in different ways, but you can do the matching in lots of ways, stratified matching, all sorts of different types of matching. Just to note, of course, even in a randomised control trial, there are potentially going to be differences between covariates for treated and control groups, just because you're working with a finite sample. And similarly, in propensity score, the covariate balance here is a large sample property. Now, there have been lots of papers against PS matching, particularly King has got a bee in his bonnet about propensity scores. But you can do all sorts of other things. You can, as I said, stratification that I won't go into. You can also look at, so the idea then of how we might use this propensity score to estimate our treatment effect is to weight your sample using the propensity score, if you like, to obtain a new weighted sample. And then you can just estimate the average treatment effect. It's really easy to run expectation through this to show that it's unbiased. And then this is the estimate of your average treatment effects of the treated if you want to use it. But this is all very standard, simple maths. Now, you can actually also use it in continuous treatments, and a nice series of papers by Hirano and Imbens and others, where now we just have the same thing basically running through, but now you have a continuous treatment instead of treated or not treated, and you have similar kind of constraint, you have a similar kind of set of conditions for strong ignorability. And you have to have this common support idea. So instead of the propensity score not being 0 or 1, you basically just have to have this condition here, that your continuous treatment given your propensity scores is never zero, the probability of that. And then of course you can get your treatment effects for any particular dose, if you like, that's now continuous. So the work that I was then doing, the kind of papers analysing the data that I was talking about earlier, basically just building a model. Okay, so my setup here, because our concern was always that, well, a lot of this propensity score stuff assumes that you've measured all of your confounders. Undoubtedly, that is not going to be the case in the kind of data that I'm working with. So we were trying to look at the impact of these unmeasured confounders. So let's imagine we've got unobserved covariates U and W, because we're always going to have unobserved covariates, but not all of them are going to be confounding. But let's imagine that the UIs are confounding. So in this case, we need to have there'll be our covariates that we have measured and our confounding covariates. Then we'll have this statement that Y is conditionally independent of treatment given our covariates and that we have measured, and the U's, the W's don't matter because they're not confounding unmeasured covariates. And then we just can specify whatever regression model we like, doesn't matter. But the point is actually we also throw in a random intercept, so that can capture some of those group level effects. Yeah, so the idea was that we can try and capture some of this unobserved confounding via a random effect, by a random effect model, because it's going to adjust for some potentially unobserved time invariant heterogeneity in your data. Now, of course, then, so this is a paper that we published, kind of Dan and I kind of wrote a few years ago now, but we basically proved all the results that were proved for the standard PS model in these settings. And of course, you can do your bias adjustment by standard iterated expectations. So I want to work out my expected value of my treatment at some dose. You can just get at that by using the conditional, by running your expectation over the conditional expectations of your covariates in the standard way. And then you can add your U and W, which are your unobserved and observed covariates, by throwing in this, your propensity score here, which you've modelled. In fact, yeah, if you've got, again, you need to here have W in this model here for this to hold, so you have to have estimated your propensity with your unobserved, your non-confounding, your confounding variables in the model. So you have to still have those. You still have to have the assumption that you've used you've used all your confounding variables. So I'm not going to go into this in too much depth, so we've got 15 minutes left, but you can kind of run a simulation model of all of this. And you can see, so I should probably just say in terms of what all of these are. So of course, we've run a simulation study with observed and unobserved covariates, and then we fit the model, and then you can work out a propensity score model, assuming that you've got a correctly specified model. You can use the model where you exclude the confounder UI, so we can pretend we haven't used it in our data because it is after all unmeasured. And then the one that we developed is this generalized propensity score in this longitudinal model that included a random effect. And in fact, it did pretty well. So obviously you're going to expect this first set of data to do best. Right? This is the data where you're assuming you've got all the data and you're using the true model that you simulated from. And then this is the more standard propensity score model. And then this is the model that we used where we threw in a random effect to try and mop up some of that unobserved covariates through the random effect. And you can see that we do quite a bit better. The truth, particularly when the doses are high, but the truth is 2.74, and we do okay in our model, and it does particularly badly in the standard propensity score model. So, and the coverage also is close to 95%. This is where we've assumed that we've got 5% on the significance. So we kind of demonstrated it worked, and then we were applying it to this effects of road capacity expansions. So this constant obsession with building more roads, particularly in the States. So this data actually came from the US, and we had fun with this because I don't know anyone here that works with data. Getting good data sets is quite entertaining. So it took us probably about a year actually to pull together the data that we felt that we needed after we'd drawn our DAG. And even then there was a lot of data that we couldn't get hold of, but nonetheless we got huge amounts of confounders. So we got all sorts of data on congestion and volume. We ran this in the States because the States has better, they've got a massive mobility data set, which is also great, fun to play with. At that point they were better at kind of gathering transport data than we were in the UK. We're very good with accidents, we're less good with actual traffic data here. So we pulled together a whole bunch of confounders, including, and then we have a whole bunch of unobserved confounders that we didn't put into our model.
Did you use, I mean, equilibrium models like the Brest paradox where you increase capacity and get worse?
Yeah, so well in fact, no, actually what we did show is that as you increase your capacity, then, so we kind of showed that you do still get an increase, so we were looking at kind of traffic flow, and it does improve if you increase capacity, but not to the extent that you might expect, right? So the percentages are kind of quite small. So if you look at, for doses of less than kind of 2 here in terms, this is capacity expansion, right? Then you get quite big increases, but it kind of flattens off. So if you increase too much, then you're not getting much benefit in terms of the traffic flow, not surprisingly, right? But if you looked at some of the projected road expansions that were planned in the States at the time, were just ridiculously beyond those. So this actually kind of was work that Dan was doing at that point, you know, because he does quite a lot of policy work with the kind of the US and the UK government. So basically, this was answering a particular question that they had. But in terms of congestion, they don't necessarily help. So the first one was traffic flow. But if you're thinking about congestion, then you don't really get significant. You don't get significant effects. Even when you really kind of have you get a bit of an improvement, but then it's back down to having no effect really in terms of the congestion. Again, not surprisingly, right? It is as you might expect, but these are quite small capacity expansions, right? So in fact, I think that they were thinking that these kind of effects would be seen at the more like 10-15% rather than 2-3%. And then kind of the final one I want to talk about is I mean, hopefully this is one I've done quite a few of these kind of, I think this is child pedestrian casualties related to deprivation. And again, you know, as I said, we've got the data. We've also got quite a lot of data in London by kind of based on kind of demographics at various levels that are to do with the census data, plus others at these kind of ward level. And so again, this time we played around with using what's known as a doubly robust method, where you have an outcome regression model and then you also have a propensity score model and you combine them. And the idea is that if your outcome regression model is correct, you'll be unbiased. If your propensity is measured correctly, you'll be unbiased. And it gets the benefits of both, really. So we assumed that we assumed both an OR and a PS, an outcome regression and a propensity score model, to create this doubly robust model. And then we had to do a whole bunch of other stuff that I won't go into here to actually do the analysis. So we just did an approximate Bayesian analysis of this, and this is the data that we used. So we had huge amounts of data. Again, we spent. In fact, it's going to be interesting because I've arrived at LSE and I was so used to having all of the kind of compute power at Imperial, and I'm sure it's the same here. But I'm thinking I'm not going to be able to. At the moment, I've just got my laptop. It's a bit of a nightmare, and I can't do any of my analysis. I'm going to be relying on Dan to do all the kind of data crunching, having no longer access to the grid at Imperial. So we have lots and lots of data, but actually, child accidents have been dropping, right? So child pedestrian accidents have been dropping. There have been some good interventions. London, we've done another analysis on the 20-mile-an-hour zones as well, looking at the kind of improvements. So there have been loads of interventions to help reduce these accidents. But we did, I'm going to just jump straight to the kind of the punchline really. We did see that deprivation is something that's, again, it'd be quite interesting to talk to colleagues at LSE actually. So there is this index of deprivation that we use as a proxy for deprivation, but I'm sure that, and that's built up from a whole load of other things from my understanding, but I think it's a very hard thing to measure. But we did show that you do see more child pedestrian accidents in areas that are where there's more deprivation, and I guess not surprisingly, but we were surprised at the level, because if you look across London from the highest to the lowest zones of deprivation, you're getting twice as many child pedestrian casualties, which is clearly kind of not acceptable. And I think a lot of it is around infrastructure and lack of investment in those kind of areas. So I guess really my conclusions are, I think we need to just think really carefully about how we do these observational data analysis. The kind of levels of bias that you can get are quite scary, and I think without education and without mathematical and statistical understanding, you can really jump to the wrong conclusions. And there is so much data out there now that's observational, that isn't designed, that doesn't come from wonderfully designed experiments, and I think that we just need to be more careful. But of course there are lots of limits with the propensity score method as well. It's just one way of thinking about it. I do have a final comment before I finish, in that so when Adrian Smith took over as president of the Royal Statistical Society, he went through all of the red papers. We're much nicer to each other now, I should say, but he went through all of the red papers. For those of you that, mathematicians actually are generally nicer than statisticians. And I've seen this when I've been on panels at EPSRC. The mathematicians are all very supportive. The statisticians are just cruel to each other. Blimey, we need to be nicer to each other so that we can get grant income. Anyway, and I keep saying this, whenever I'm on a panel, I'm kind of saying, let's just make sure we balance the fact that statisticians tend to be quite critical of each other. Anyway, I can talk about that for a while as well. But the Royal Statistical Society used to have these red papers where you'd get somebody that was positive about the paper and then somebody that was more critical. Some of the published stuff, if you go back through their journals, is quite terrifying how cutting they were to each other in the responses. So this is now a paper that was in Series A in the 80s, and it was all about the effect of seatbelt legislation, which is clearly a good idea, right? And they did a big analysis of it. This was Harvey and Durbin, fantastic kind of statisticians that knew what they were talking about. And then if you go and find the discussion, Ehrenberg here, he writes this incredible thing. Here we go. This is recorded, isn't it? But I'm going to read it out anyway. This really is a dreadfully vapid paper. This is published, you can find it. Full only of intellectual masturbation. Can you imagine? The danger is that younger statisticians often think such performances sophisticated and ape them. I mean, why did the authors not simply report that all of their time series mumbo-jumbo made no difference? He was basically advocating for, let's just take number of accidents before, number afterwards, and be done with it. Now, of course, Harvey and Durbin, if you know either of these characters, can really rise above all of this. They can rise above all of this. So they said, it is difficult to respond to Professor Ehrenberg's tirade, since it contains little in the way of relevant rational argument. Anyway, so I think that the fact that a simple before and after comparison sometimes gives the same results as a model which allows for a trend and explanatory variables does not mean it always gives the same results. And with that, I will end just by saying I could not agree more with the wonderful Harvey and Durbin, and